Let us derive the Laplace and Poisson's equations from Gauss law. Gauss law states that the total electric flux leaving a closed surface is equal to total charge enclosed by the surface. Accordingly, integration of d over a closed surface S is equal to Q. Here, Q is the total charge enclosed by the surface S. We know that any closed surface encloses volume. So, if we consider an arbitrary closed surface S, then it encloses volume V. Then the charge distribution within the volume would be volume charge distribution of density rho V coulomb per meter cube. Therefore, Q can also be expressed as volume integral of rho V. Therefore, Gauss law becomes surface integral of d over the closed surface is equal to volume integral of rho V. This forms the integral form of Gauss law. We shall obtain the point form of Gauss law from this equation because in electromagnetics, the most used equations are point forms or differential forms. So that's why we shall convert this integral form of Gauss law to differential form of Gauss law. So for that, we have to remove integrals from both the sides. So for that, we need to convert any one of these integrals to the similar to the other side. For example, the closed surface integration can be converted to volume integration or vice versa. So we know that divergence theorem is used to convert a closed surface integral to volume integral and vice versa. That is, the divergence theorem in D is given by surface integral of D over a closed surface S is always equal to volume integral of divergence of D throughout the volume. This divergence theorem is mathematical theorem which is applicable for all vectors which have partial derivatives. D is also having partial derivatives with respect to the three space variables. So that's why divergence theorem can be applied to D. So here, if you carefully observe, the left side LHS of the divergence theorem is same as LHS of the Gauss law. So that's why the LHS of the Gauss law can be equated to RHS, the right hand side of the divergence theorem, so that both the sides of the Gauss law will have similar integrals. Therefore, the left hand side of the Gauss law now becomes volume integral of divergence of D, which is equal to volume integral of volume charge density. The integrals are applicable to larger spaces. That means for volumes or surfaces or lines. But if you are interested to apply any particular theorem or law to a particular point or a smaller dimension, like differential length, differential surface, or differential volume, then integrals are not required. So, for considerably small volume containing the charge, The Gauss law can also be expressed as delta D into delta V is equal to rho V into delta V. Here delta V is the incremental volume or smaller volume element containing the charge of density rho V. So for this particular small volume element, no integration required. Still, the relation holds good. If this volume considered is same for both the sides of the equation, then delta V can be cancelled on both sides. This Gauss law is applicable to single system, so delta gets cancelled here to give us a very useful relation del dot D equal to rho V. This equation is Gauss law again, but in point form or differential form. Differential form. That means this relation is applicable to any point or any smaller volume or any volume enclosed by small closed surface. That's why it's called differential form or point form. And this is most useful compared to the integral form of the Gauss law. And this is also popularly known as the Maxwell's first equation. So we can also take this discussion as the derivation of Maxwell's first equation from Gauss law. Now we shall proceed from this point form of Gauss law to Laplace equation. In the Laplace equation, we would like to explain the potential distribution in a system. So that's why I would like to convert the electric flux density D to electric potential V. So for that, I'm going to take up these steps. I convert D to electric field intensity E. And we know that the relation between D and E is this, D equal to epsilon E. So from this E, I'm going to get you the electric potential. And here also, we know that electric field is related to electric potential through gradient. So using these two equations, I can convert easily the D to V. So now, let us proceed here. We have D equal to epsilon naught E. Therefore, the Maxwell's equation becomes epsilon naught into E, which is equal to volume charge density. Now, the question is about epsilon naught, the absolute permittivity of the medium. Is this epsilon naught constant? It is yes, if the medium is homogeneous. That means the medium in which electric field is distributed, charge is distributed, is homogeneous, then epsilon naught can be taken out as a constant. So that's why I would like to write that for a homogeneous medium, homogeneous medium is a medium in which the electrical properties of the medium remains same everywhere. For a homogeneous medium, epsilon naught is constant. So therefore, the next part of the relation becomes del dot E, divergence of E is equal to rho V by epsilon naught. This is one of the important relations here. let it be equation number 1. Now, as I said, I would like to convert electric field to electric potential using the gradient relation. Electric field is given by the relation E equal to minus del V, negative gradient of potential. Therefore, equation 1 becomes now, therefore, equation 1 del dot E in place of E, we shall write minus del V, that is equal to rho V by epsilon naught. This is from equation 1. Now, del dot del. Del is a vector. It's a operator, but vector. Del dot del is a scalar product. So, we are going to get del square V. Here, del square is a scalar quantity, which is equal to minus rho V by epsilon naught. This is equation number 2. The equations 1 and 2 are called the Poisson's equations. The equations 1 and 2 are called Poisson's equations. Poisson's equations. So equation 1, we can observe it for a while. Equation 1 contains electric field E. So left hand side of this equation is divergence of E. That means distribution of electric field, divergence, distribution of electric field in a region where charge is present. That is given by rho V. That means if there is a electric field and also there is a charge distribution within the electric field of density rho V, then E can be found. The electric field distribution in the complete volume can be found using the equation number 1, the Poisson's equation. Similarly, in the same region, potential distribution V can be found by the equation number 2. So in summary, from equations 1 and 2, the Poisson's equation give electric field distribution and electric potential distribution in a region where charge is present. So in a charged region, field distributions are given by Poisson's equations. There are many systems in which fields are present, but they do not contain any charge distributions. In such a case, we can place rho V equal to 0 in above equations for a charge-free region. A charge-free region, rho V can be equal to 0. Therefore, equations 1 and 2 become del square V equal to 0 and del dot E equal to 0. So these two equations represent charge-free region, where field is present. So these equations are known as Laplace equations. In summary, the Laplace and Poisson's equations give the potential distribution and electric field distribution in a region. If the region contains charge, then Poisson's equation is applicable. Otherwise, Laplace equation. Let us understand these equations with respect to some examples. Let us consider a parallel plate capacitor. So we know that a parallel plate capacitor contains two parallel conducting planes. Both are holding charges. One positive, another one is negative. And this charge distribution is surface charge distribution of density rho s, let us say. Now, this surface charge produces electric field between the two plates. So between the two plates is a dielectric medium. So we know that if the dielectric is perfect dielectric or perfect insulator, it doesn't hold any charge. So that's why this region do not contain any volume charge distribution, but electric field is present because of the surface charge. And this is the direction of electric field. And we know that electric field is always perpendicular to metallic surface at the boundary between conductor and dielectric. So since the field do not contain any volume charge here, this is called Laplace region. And Laplace equation is used to find electric field and potential values. Similarly, I would like to give one more example. Let us consider another example. Consider a concentric cylindrical system or a coaxial system. Generally, in coaxial cable, one of the cylindrical conductor is grounded, holding a potential of 0. So generally, the inner cylinder carries a positive charge on its surface. So it's a surface charge of density rho s. Between the two cylinders, we can find a dielectric. This dielectric also contains no charge, and electric field is having radial direction. So the electric field is distributed between the two cylinders. Since here also no charge in the field, this is also a Laplace region. If these two regions, that is the regions of parallel plate capacitor and coaxial cable, contain some charge, that time the same systems become Poisson's systems. A very good example for a Poisson's system is a p-n junction or a semiconductor diode. So in a p-n junction, we know that there are two regions which contain free charge carriers. But both the regions are electrically neutral as the number of electrons and holes in that region are same. But there is one more region near the junction called depletion region, in which we can find uncompensated charges or immobile charges, which are the atoms bounded by the covalent bonds. They cannot move. In this region, charge is present, but free carriers are not available, hence the name depletion region. So because of this stationary charge here or static charge, electric field is produced near the junction. And the direction of the electric field is from positive charge to negative charge. So this is an opposing field for the flow of positive charge, that is holes from P region to N region. If the holes are moving from P to N, this electric field opposes. We know that one. This is the barrier created by the field. So the depletion region is a region which is containing charges of density rho v, coulomb per meter cube, and also electric field distributed within the charged region. Hence, this region is a Poisson's region. A Poisson's region. So these three examples will give you some insight in identifying the Poisson's and Laplace regions. So that's about the discussion of Laplace and Poisson's equations. Thank you.